My name is Megan Mishra, and I'll be talking about the third Physics 2211 lab about black holes. To start, the purpose of the lab aligns with each part. Part 1's goal is to use a computational model of a star orbiting a black hole to find that black hole's mass. The result ends up being that the mass is 1.43 e34 kilograms. Part 2's goal is to create a computational model of a spaceship that approaches the system in Part 1, lands on a nearby planet, and then takes back off to orbit around the black hole. It's also to calculate the initial velocity needed for the ship at launch to orbit the black hole while avoiding being sucked in it or crashing. The initial velocity will end up being negative 5.1 e7, 3.6 e6, and 0 meters per second. One of the two main physics principles present in the lab is Newton's second law, which concerns the system and the surroundings, namely that the force that acts on the system from the surroundings results in changes of momentum. In the image here, we can see the formula for the momentum principle, which states that the net force is equal to the rate of change of momentum. Using this and the knowledge that the net force is equal to its parallel and perpendicular components, we can then say that the total rate of change of momentum is equal to its parallel and perpendicular components added together. The second key physics principle is Newton's law of universal gravitation, which concerns the attractive force between any two objects with mass. The equation can be seen on the right and can be rearranged to solve for the mass of an object. We're told that for the sake of this lab, the net force is equivalent to the gravitational force. So we can assume that the gravitational force is equal to the rate of change of momentum. From there, it's possible to substitute that value into the equation. So if we know the rate of change of momentum, we can then solve for m2, which in part 1 is equivalent to the mass of the black hole. For the first computational model, the system is the black hole and the surroundings are the star. The initial conditions consist of a seed for the star and black hole, which is generated using my email, and the gravitational constant capital G, the mass of the star, which was given to us, and the time interval, which is a day represented in seconds. We begin at t equals 0. To code the model, we had to first define initial and final velocities. From here, we can find the initial and final momentum vectors, knowing that momentum is mass times velocity. We can then calculate the change in velocity and momentum, and from there calculate dp dt, or the rate of change of momentum. This is equal to the net force. We can then calculate the parallel component of dp dt, which is equal to the parallel component of the net force, and from there we can calculate the perpendicular component of dp dt, which is equal to the perpendicular component of the net force. We can then calculate the mass of the black hole at each point in the calculation loop, and then because there are multiple values, we can sum it up in order to average it. Here is the computational model at two different points in time. The vectors represent both components of the net force, parallel and perpendicular, as well as the total net force. The results show us that the final magnitude of net force is 9.07 e28 newtons, and the calculated mass of the black hole is 1.4 e34 kilograms. The observed orbit of the star around the black hole was elliptical. This orbit is due to the net force acting on the star, which in this case is solely comprised of the gravitational force. When the star is closer to the black hole, it has a higher mass, and when it's further away, the mass is lower. This is due to the gravitational force being higher near the black hole and lower when further away. There are fewer sources of error than normal because this is just a computational model as opposed to an experiment. However, the final mass of the black hole may be slightly inaccurate as it was averaged from rounded off numbers. For part 2, the computational model system is a spaceship and the surroundings are everything else, namely the star and the black hole. Initially, the mass of the black hole is the same value as obtained from part 1. The initial values are constant, namely g, the mass of the planet and the ship, and we begin at time t equals 0. Then, the initial velocity in the x component is negative 5.1 e7 meters per second, and the y component is 3.6 e6 meters per second. This will be discussed more shortly. We can then use the knowledge of the law of universal gravitation to code the values of the force of the black hole on the planet, the force of the ship on the planet, the net force of the planet on the planet, the force of the black hole on the ship, the force of the planet on the ship, and the net force on the ship. We also need to make sure to apply the velocity and position update formulas in order for things to move as seen here. As you can see by observing the trajectory of the ship, which is represented in magenta, using these values the ship is able to successfully avoid colliding with the planet, whose orbit is in cyan, and the black hole. We can see this closer up here. The initial velocity needed to fly around the black hole without crashing on it or the planet is negative 5.1 e7, 3.6 e6, and 0 meters per second. This was calculated through trial and error, though we could assume some things. The x component had to be negative, and the y component had to have a smaller magnitude than the x component. This results in motion that's left and upwards from the planet. The gravitational force from the black hole on the spaceship increases as the spaceship gets nearer. This causes the speed of the spaceship to increase when closer to the black hole. This computational model could have some error due to the mass of the black hole being rounded off from the computational model in part 1. So in conclusion, we can discuss what this means. The net force is equivalent to the rate of change of momentum due to the following formula. If this is true, then the components of net force in the parallel and perpendicular must also be equivalent to the components of the rate of change of momentum. And what if, instead of leaving the black hole, you wanted to enter orbit around it? What initial velocity would be needed? We can solve for this through knowing that the x component needs to have a smaller magnitude, while the y component needs a larger one, the opposite of the initial situation. Using trial and error, we can find that with a velocity of negative 1.1 e6, 1 e7, and 0 meters per second, we can find a trajectory that orbits the black hole. The trajectory is seen as magenta.